recording. All right, good. So, welcome to today's class. In our previous class, we introduced linear regression, where we defined linear regression, and also we saw that is the variables which make a linear regression equation. If you can remember, we talked about the independent variable or the predictor variable, also the inputs of the model. We also discussed about dependent variables, that is the y, or the output which we are expecting. Okay. We also discussed about the coefficients of the equation. Okay, whereby we saw in a simple linear regression we usually have two constants. Okay, that is the slope or the constant attached to what, to x variable, which is also known as coefficient of what, of variable x. Okay, also we saw another constant which is the y intercept. Yes, correct, it is the y intercept. And if you remember, for the y-intercept, we said it might be a positive, okay, intercept, or a negative intercept. Okay, it can be a positive intercept or a negative intercept. That's why when you are writing that is the model, it's always to write that is plus or minus. That is the C. Okay. All right, let me just illustrate what I mean. Okay, so remember we've said the model can be what? Can be, that is the y-intercept can be a positive, it can be a positive intercept. Okay, why? Because under the positives, this is x, okay, positive x, remember that. And this is what? This is negative x. Okay, we have y and we have negative what? Negative y. So if we extrapolate this, that is uh, regression line, you can see it will come to cut the y-axis on the what? On the positive side. Okay, that's why I'm saying that the value of c can be plus or minus c. Okay, that is y is equals to mx, okay, plus or minus c. Okay, meaning for c it can be a constant value or it can be what? A negative value. So in this case we'll have what? We'll have that is our y-intercept will be a positive value. Okay, so in this case we will say that is y is equals to mx, okay, plus c. Okay, what about maybe for a case where maybe the regression line passes through what, that is the negative. Okay, let's assume this is negative y, we have negative x, we have y, okay, and we have x. Okay, then we have a line, that is a regression line, which cuts, that is the y-axis. If we extrapolate this, you'll find that that is this regression line will cut, that is our y-axis, at what? At a negative, that is side. So in this case we'll say that is our y will be mx minus what? Minus c. Why? Because you can see it cuts that is the y-axis on the what? On the negative side. Okay. All right. So we gave an example of a model which was that is salary and experience. Okay, like creating a model between salary and Yes, Aim, you have a question?
Yes, sir.
Yes.
Good evening, everyone.
Good evening.
In some scenarios,
Mm-hmm.
that you have a C intercept. Let's have an equation which is y equal to mx plus c, where the linear regression has generated a constant c, which is a negative, and the nature of the variable doesn't allow the negative value at the intercept. For instance, let's calculate the weight of the person. The
Uh-huh.
weight normally doesn't be a negative value.
Mm-hmm.
But however, the equation calculated using that linear regression comes as a negative. How
Mm-hmm.
do we handle that problem?
Okay, about that. Okay, good. Because the example which I'm going to give you, it's an example of that is rainfall amount. Of course, we can't have negative rainfall amount. Allow me to answer that during that period. Okay, I will show you how we will treat that. Okay, because I'm going to use an example for rainfall amount and the umbrella cells. Okay, so I will come to do what? To illustrate that is whenever we have what? Whenever we have a negative value of what? Of y-intercept. What? How do we that is use that variable? Okay, so I don't want to exhaust it at this level because it's something we'll discuss. So you will just allow me to that is answer that during that period. Okay, so we can continue. So we have the salary. We had given an example of salary. Okay, salary and yes, in terms of experience. We'll also do another one whereby we'll create a model to predict the number of umbrella cells. Okay, okay, umbrella cells. Okay, given what? Given the amount of rainfall. That is, let's say A multiplied by what? Rainfall amount. Rainfall amount in what? In millimeters. Okay, plus or minus C. So this is the model which we'll use. Okay, I guess I shared the data set and we will, for these examples, we will use that is the rainfall amount data set. And then maybe if you want to try it, or that is all to do using another example, now you will use the income and expense example. Okay, but for my case I will use umbrella and rainfall amount for, that is for illustration. Okay, all right, let's now continue with our, we also discuss about types of linear regression, that is simple linear regression, multiple linear regression. Okay, so we talked about also the that is the how, like the presentation of the line. Okay, of regression, we might have a positive linear relationship and also negative linear relationship. If you can remember me drawing that is a graph which looked like this, and also another graph which looked like this. Okay, and we said for this case, whenever maybe one variable is it's increasing, let's say x increasing, then y, you can see y is also increasing, so y will increase. So in this case we'll have a positive linear relationship between the two variables. But in this case, we say that as one variable increases, the other variable is what? Is decreasing. And this we said is an example of what? Like it's a negative linear relationship. Okay, like one variable is decreasing as the other one is what? Is increasing. Okay, yes, so that's what we covered under linear regression line. Okay, so now finding that is the best fit line. Okay, how can we get the best fit line? And when we are talking about the best fit line, we are talking about like a linear or a regression line. Okay, we are talking about a regression line which will fit, okay, more than 90 of what? Of our data sets. That is our of our data points. Okay, let's assume we have these data points which I've plotted. Okay, so this is one of the, that is a regression or the line of best fit. Okay, this is an example of that is a line of best fit, and also we can have other one. Okay, with that is some values or some data points that is far from the what? Far from the that is the regression line. Okay, so definitely when we will be measuring, that is our next topic. When we'll be measuring the goodness of fit. Okay, these are some of the aspects which we will look at. Okay, like for example, I'm assuming this that is this best of line takes 90 percent of what? Of our data points. Like 90% of our data points are within what? Are with along this regression line. Okay, but in this case, definitely you can see more. We have very many points which are outside the regression line, and they are even far away from the what? From the regression line. Okay, so in this case, you might find this that is a regression line, all this line of best fit only takes into, or only all these model only models 40% of what? Of our data. Okay, so meaning the other data we cannot explain about them. Okay, they are outside the what? The regression line. Okay, so in this case we will also to try to determine how we can have that is a line of best fit. Okay, yes, and we can minimize this, maybe given a data set. You can minimize this by removing some outliers. If at all you have very many outliers, then you will have to that is the remove those outliers. Okay, all right. So when we are talking about best, that is finding the best fit line, we are saying when working with linear regression, of course, our goal is to find the best fit line. That means the error between the predicted values and the actual values should be what? Should be minimized. Okay, that is the difference between the actual values, that is y i's minus y at. Y at is the predicted values. Okay, and y at can be y at can be what? Can be equal to maybe a x plus what? Plus c. Okay, so basically what we are saying, it's the what? The error term. Okay, that is the error term will be y i's minus a x plus c. Okay, this is the predicted values. So what we are trying to say that for us to have that is the best line of it, we should have a very small value of error. Okay, or we should be have a very minimized that is error term. Okay, or a small value of what? Of the error, that is between the actual values and the predicted values. Okay, so the best fit line will have the least error. You can see the best that is a line will have the least what error. All will have the smallest error. Okay, that is, and the error which is close to zero. Okay, all right. So the different values of for weights of the coefficient of lines gives a different linear regression. So we need to calculate the best values of the what of our coefficients for us to find the best fit line. So to calculate this, we use a cost function. Okay, that is for us now to come up with the line of best fit. Okay, we also have to come up with what? With the best coefficients. That is, let's say a0 and a1. Like for example, we are saying y is equals to a0 x, okay, plus or minus a1. So our objective is to come up with what? With the best values of what? Of the coefficients. And one of the methods of use that is of coming up with the best coefficients is using cost function. Okay, so cost function tries to minimize that is the it tries to minimize the 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 distance or the error term. It tries to minimize the error term. That is cost function. Okay, tries to minimize the what? The error term. Like it is trying to minimize this distance, all these differences. Just to illustrate. Okay, just to give an example. Like to it tries to minimize the what? The error term. Okay, all right. Now we have the cost function. Okay, so that is the different values of weights or coefficients of a line, or that is of lines, give the different line of what? Regression. And the cost function is used to estimate the values of coefficients for the best fit line. Cost function tries to optimize the coefficients or the weights. So cost function, okay, basically does what? It optimizes the regression coefficients or the regression weights. Okay, and it measures how a linear regression model is performing. We can use the cost function to find the accuracy of the mapping function, which maps the variable to the output variable. Okay, so for linear regression, we use this cost function. This is mostly of our cost function. Okay, to optimize what? To optimize the that is to optimize um, the the coefficients, okay, all the weights. So mean squared error, okay, that is MSE, is one of the most used that is cost functions. Okay, so which is the average of the squared error occurred between the predicted values and the actual values. Okay, it can be written as, now that is the how we write the cost function. Okay, so the cost function we usually say, let me clear some space here where I can illustrate. So for cost function, we are saying that it is the mean squared error. So in this case, we are going first of all to do the summation, or we are going to square the error term. Okay. So because we are having many values, okay, of course, let's say x eyes, okay, or maybe y eyes. We are talking about now y eyes, that is as our outputs. So minus, okay, y at. Remember why I've said it is what? It's the predicted values. Okay, this is the actual values. These are the predicted values, and you can see all these will be what? They will be a positive value. Okay, why? Because we've squared here. So in case, even if we get that is the high value in comparison to that is to the actual, meaning it will be a negative, then it will be what? It will be squared. Okay, yeah, so that is summation of that is y i's, okay, minus that is y at. Okay, so summation of y i's minus y at, divide by what? Divide by n, or equal, that is 1 over n, okay, summation of y i's, okay, minus what? Y at, okay, squared. In this case, we are saying that this is for if maybe we are doing like a population data, okay. So in this case, we can also say it is 1 over n summation of y i's, okay, minus maybe the model a x plus what? Plus maybe b squared, okay, like it is here, okay. So this is the what? This is the linear equation for that is mean squared error, okay. All right, so then we have where n is the total number of observations, okay. Then y i's, they are the actual values. Then we have a1 xi plus a0, it's the what? It's the predicted values. We also have what we call residuals. Residuals are also known as y deviations, okay. They are also known as error term, okay. The error term, the y deviation, that is the is it the y? The y deviations. Yes, the y deviation or the error term. So that is the residuals. It's usually that is the distance between the actual value and the predicted values in is called residue. If the observed points are far from the regression line, then the residual will be what? Will be high. Okay. So cost function will be what? Cost function will be y. So in case that is our data points, that is our observations. Okay, you can see. In case our observed points are far away from the regression line, okay, then the residual will be what? Will be high. That is the distance between the regression line and the that is the predicted values, okay, will be what? Will be high, okay. And if it is high, then definitely the cost function will be what? Will be high, okay. And if all these will be high, so if the scatter points are close to the regression line, or if the scatter plots are close to the what? Regression line, then the residual will be small, hence the cost what? Hence the cost function. So here, for us now to optimize or to use that is cost function, it is to try that is our model, okay, or our data are almost within what? They are almost within our regression line, okay. That is in case maybe you have any outlier which might that is might bring that big discrepancy, or that which might shift the line of best fit. Okay, we can now do what? Do away with what? With that outliers. Okay, and just maintain that is a data set which um, it's okay, like free from the extreme high and that is high and small that is values. Okay, for us now, meaning our data points will be almost along the regression line. Like for example, that is our data points. Okay, let's assume this is our regression line. Okay, okay, so you'll find even after doing your prediction, okay, some or most of the values will be what? Will be close to the what? Will be close to the regression line. Okay, that is let me that is most of your values will be close to the what? To the regression line. Okay, in comparison to maybe when they are what? They are not close to the regression line. Okay, okay, all right, okay, good. So that's the residuals, basically the difference between the actual value and the predicted value. Okay, and that is the higher or the bigger the value of that is the residual value. Okay, that is the higher the cost function. Okay, and we usually like we love our, or we say that is our model, it's good if our cost function is kept at low. Okay, if our cost function is kept at low, even close to what? Close to that is a zero. Okay, yes. I hope we are all together. Yes, Elizabeth.
I think we have not been together for, for past few minutes.
Okay.
Because I'm trying to understand the difference between the predicted variable,
Hmm.
is it, or value, the predicted value, and the yi,
So what
the
is
the yi and the y at. Because I was, let's say if you're working with variables,
mhm.
I thought those variables are already our why eyes, like why, where are we now getting this and starting trying to find this, the predicted variable.
So like for example, let me just show you an example. So check out that is on this data set. How many variables do we have here?
Two.
Okay.
Yeah.
That is rainfall, which is
And
our x
umbrellas.
variable, and y, which is
Why?
what?
Yeah.
Our y output. That is our i's. These they are our yi's. Okay.
Yes. Yes.
What if maybe we were to predict, given maybe now, given another set of maybe amount of rainfall. Okay. So what I might take, maybe I will, what I can do is just a minute. What I can do, let me try to generate that is I can try to maybe get the average. Okay, I might decide to take the average of this. Okay, and this say this is what we are expecting our maybe our rainfall trend to be this. Okay, our rainfall to be this. Then what will be this? If we calculate the values of what? of y here. What will
Mm-hmm.
be the values of these y's? Maybe these we are predicting for the year 2018.
Okay. Meaning we have to find out.
Yes, so first of all, meaning that's why you can see now the predicted what? The predicted values, okay, as we
Mm-hmm.
said, must come from this linear equation, which that is the equation which will y- create using the available data, okay, for
Mm-hmm.
us now to do what? To do a projection. So these will be our predicted values, okay? And
Mm-hmm.
these are our historical data. So basically, for us to predict all this, we must use what? A model. That is AX plus or minus maybe B.
Yeah.
I
Mm-hmm.
don't know if that's clear. You will
Yeah,
see
it's
that. You
clear.
will see that when we'll be doing the prediction. Okay, you will really see that. Like for example, um, just an example. Remember, we have very many, like three, that is ways of uh, doing prediction. Just a minute, I just want to show you something. So, basically, okay, let me also add something. I need just a minute. Don't worry, I will still as well come to this part. Okay, so let's assume this is what? This is our regression what? This is our model, okay? Which we will now use, okay, here to predict what? Our maybe the umbrella cells. Given that is the we are assuming the amount of rainfall will maybe pick the same trend, okay? We are assuming that is the that is given that is amount of rainfall of 84.5 millimeters, okay, what do we expect to do what that is the all what how many umbrellas do we expect to what to sell? So in this case it might be now you'll take your model here which is 0.4482, okay, multiply by now, okay, our what? This is our value, that is our x values, minus 18.915. Okay, so basically, roughly we'll do what? We'll sell, that is, we might sell 19 umbrellas. Okay, we might sell 19 umbrellas. And if you check between, that is 83.2 and 84.5, you can see the model might be that close. That is the difference will be what? The difference will be plus or minus 2. Okay, but we usually give it a dot of plus or minus 5. Okay, so you can see in this case that is we've predicted. So this is our y at. Okay, this is a value of our y at. Okay, even from the model you can try maybe to from the model as well. Someone might try to use now the model to create what? Like to extrapolate and see maybe, okay, so we have the function, maybe to move it forward, okay, by what? By let's say 10%. Okay, if I move it forward by 10%, what will happen? You can see it is trying to come up with what? Like it's predicting like or it is extrapolating the what, the regression line. If maybe we do it by, let's say, 90%, you can see how the model maybe will look like. Okay, but now for us now to get the data points here, we might have to do what, to do some that is some projection given that is our x values. Okay, as well as maybe if you want to extrapolate it or forecast backward. Okay, if you want to forecast it backward, we can say we want it 90%. Okay, and you can see the way the model, it is kind of that is predicting up to this end. And you can see this is our y-axis. Now the line, you can see the line after extrapolating, the line where it is cutting what, it is cutting the y-axis, and you can see it is around negative 19, which is negative 18.9, which is almost negative 19. You can see it's not cutting that is the y-axis at 20, but at a 19th value. Okay, but we'll come to this. I hope that's clear.
Yeah,
uh,
so does that mean in this the mean squared error cost function,
uh-huh,
when you're trying to minimize the error in these functions, in those the model,
uh-huh.
does that mean for that function, that formula where we have the yi, we are going to, because we already understood where you're getting the y at
Uh-huh.
from this prediction.
Uh-huh.
So the yi's will be these ones, the one we already have our historical data.
Yes, you can decide to take maybe historical data because you don't have other available YIs. Okay.
Okay. Yeah, it's clear now. Thank you.
All right. Okay. Good. Let's proceed to that is a model performance. And basically for model performance, I said we usually use that is R squared. That is for simple linear regression. And if we are talking about that is for maybe R squared, that is for simple linear regression, and adjusted R squared for what? For multiple linear regression. Okay. R squared, we said, is also known as coefficient of determination. Okay. Coefficient of determination. So that is for simple linear regression. And if you are dealing with multiple linear regression, now you will talk about coefficient of multiple linear, that is multiple determination. Okay. Yes. So basically, the goodness of fit determines how the line of regression fits the set of what, of the observations. Okay, that is, the goodness of fit determines how the line of regression fits the set of what, the set of observations. The process of finding the best model out of various model, it's what, it's optimization. Okay, the process of finding the best model out of various models, okay, it is known as that is optimization. Okay, so it can be achieved by below method, that is R squared method. So R squared method is a statistical method that determines the goodness of fit. Okay, it determines the goodness of fit. All right, and it also measures the strength of the relationship between the dependent variable and what, independent variable. That is multiple R. If we talk about multiple R, it's when we are talking about like because if you see the strength, basically it shows what, it's talking about that is a correlation. Okay, but it's not actually correlation, but it will show us like what percent of what percent of the data is being fitted in what in our that is in our regression line. Then the I value of R square determines the less difference between what the predicted values and the actual values, hence represents a good model. So if we have a high value of R squared, okay, then it means we have a less residual or less difference between the predicted values and the actual values. Okay, so hence represents a good what model. That's how we know that is a line. It's a good or it's a line of best fit. Okay, that is if the R squared value is big or it's greater. In fact, we usually say if it is greater than 90%, it is a fairly good model. Okay, if we talk about that is, or if we get a value of 95%, then we'll say we really have what a strong model. Okay, if we get anything less than 80%, then we'll have to reconsider our variables. We will have to choose other variables, more so another independent variable. Okay, we shall also check that. We shall play with the values and see maybe the value which we'll get. So it is also called as that is a coefficient of determination or coefficient of multiple determination for multiple regression. Okay, yes. Then now I guess we'll come to the last part of that is assumptions. Okay, we'll come to the last part of assumptions, and then we'll come now tomorrow we'll do the practicals. The good thing I've already documented, just a minute, I see if I've already documented I've already done a documentation. Okay, so at least here on the practical it will be a way that is a faster thing. Okay, so in this case I used umbrella cells data. Okay, that is to do what to perform all the regression. Of course we'll come to use three methods of performing regression. Use the analysis toolpack, using a scatter chart, and also using linear regression formulas that is in Excel. And we shall that is do the analysis. Okay, and also we shall come to do what we shall come to have some predicted values. We'll do some predicted values and we'll also compute that is residuals. Okay, and see how that is the residuals that is how the residuals do what look like. Okay, that is in comparison to the data. Okay, like for example, okay, just to show you an example, that is Elizabeth. You can see this is our historical data, right? Okay,
Yes. Mm-hmm.
you can see 15 here. Okay, then we
Yeah.
have 25 here. Let's just take 15 and 25. Okay, then we have our predicted values here, which is 17, okay,
17,
and 22.
22.
Okay, so now take you can see now the residual. The first one was 15 and this one is 17, so you can see the residual. That is the actual minus the predicted. Remember this is what we did. Okay, remember
Mm-hmm.
that is we were taking, where is that? Okay, Remember here, we were taking what? In this case, we were taking the historical data minus.
The predicted value.
So in this case, we have that is there. We have the we have the 15 up there minus this
It's
17.8.
17.
So you can see the difference is minus.
Mm,
Up there
that's
we
my
had
mistake.
the second value we had
25.
25 minus 22. You can see now the value.
Mm-hmm.
I hope it makes sense.
Okay, yeah.
All right, good. So I want I want to take the next, let's say, 30 minutes to go through the assumptions. Okay, it's only these two slides, and then we will be good. That is to go. Okay, so tomorrow we shall now perform what? We shall now perform that is what we call, we shall now do the practicals. Just a minute. I connect my machine. It's almost going off. Just a minute. Okay. Good. All right. I'm now okay. So let's go to the assumptions of linear regression. Like, what assumptions do what? Like, we should assume, okay, or we should use before we can perform what? A linear regression. And basically, from the term linear, okay, we've been talking about linearity, okay, since the start of this topic, okay. So when we are talking about linear, okay, meaning we must have what? A linear relationship between what? Between that is the two variables. Okay, so for us to for us to perform a linear regression, the two variables must have what? Must have a linear relationship. Okay, that is between the independent variable and the dependent variable. Anyway, let's check on this. So below are some important assumption of linear regression. Okay, these are some formal checks while building a linear regression model, which ensures to get the best possible result from the given dataset. Okay, so linear relationship between the features and target. Okay, so linear relationship assumes the linear relationship, or assumes that there is a linear relationship between what? Dependent and independent variable. We must have that linear relationship between the two variables. Okay. Yes, last time we discussed how to, you can check what? The linear, okay, the linearity between your features. Then the second assumption is there should be small or no multicollinearity between the features. I also talked about this, like for example, more so when we are dealing with a multiple linear regression, okay, we should not have relationship between what? Between the two, that is between the two um, values. Okay, like for example, if we are using that is if we are building a salary prediction model, okay, and we are using work experience, okay, work experience in years, and what if we introduce maybe that is skills? How can we measure skills? Okay, we can also measure skills. uh, uh, Skills and experience, they are almost the same thing. Okay, when it comes to maybe jobs. Okay, why? Because we know skills comes with what? Experience. Okay, but they are two different features. What if we use those two different features, okay, to determine what? To determine that is our salary. Okay, if we use those two features, definitely we won't know. In case of prediction, we won't know which like which what, which variable it's affecting our what? It's affecting our output most. Okay, so that's why we usually say there should be more so for multiple linear regression. There should be a small or no multicollinearity. Multicollinearity basically it's the correlation, that is the high correlation between what? Between the independent, that is the independent variables. If you have more than two, okay. So multicollinearity means high correlation between independent variables. If we are talking of multiple linear regression, that is, let's say y is equals to maybe ax1, okay, plus bx2, okay, plus c. So definitely this is this and this, they are independent variables. Okay. So basically what we are saying, that is this x, there should be no high correlation between x1 and x2. Okay. As what? As our independent variables. So multicollinearity measures high correlation between the independent variables. Due to multicollinearity, it may be difficult to find the true relationship between the predictors and the target variable. Or we can say it is difficult to determine which predictor variable is affecting the what? The target variable, and which is not. So the model assumes either little or multicollinearity between what? Between the features or the independent variables. Okay, so like our more so this is that is applied when we are dealing with what? We are dealing with multiple linear regression. Okay, multiple linear regression. So for this we'll have majorly it is applicable when we are dealing with multiple linear regression. Good. Moving to the next assumption is homoscedasticity. We know we have heteroscedasticity and homoscedasticity. Okay, so for homoscedasticity, we are saying that it is a situation where the error term is the same for all the values of independent variables. With homoscedasticity, there should be no clear pattern distribution of what? Of data in what? In a scatter plot. Okay, like for example, we usually use that is these two features maybe to describe homoscedasticity. Like you might have that is a cluster, that is this cluster values distributed everywhere, and also have like following a certain what, like a prediction. Okay, like we have a certain what, a certain pattern. Like for example, let's just look it that is online and see if it is the case. We have homoscedasticity in regression. Okay, so maybe we can check. So you can see we have homoscedasticity and we have uh, yes, homoscedasticity and heteroscedasticity. Okay, For us to have a satisfying or a satisfactory model, it's the one with what? With that is homoscedasticity. Okay, in comparison to the what? To heteroscedasticity. Okay, like let me read that. Like homoscedasticity is the situation where the error term is the same for all the values in the independent variable. With homoscedasticity, there is no clear pattern distribution of data in what? In scatter plot. I don't know if this is the correct. Are we assuming that is the if we have homoscedasticity or heteroscedasticity? Let me just confirm that. Okay, homoscedasticity assumption, assumption, assumption in what? In regression. So basically, homoscedasticity, okay, refers to a condition in which the variance of the residuals or the error term in a regression model is what? Is constant. That is, the error term does not vary much as the value of the what? The predictor variable. So yes, of course. So because if we were maybe to say, if we were to say if we were to say the line of best fit will be what? Will be through these values. Okay, so you can see there is no that much clear like difference between what? Between the data points and the regression line. But here, if we were to predict, definitely this model, definitely our predicted values will be also spread all over. Okay, but for this, they will now try to what? To you to be like to be scattered in what? In a straight line. Okay, we shall also check that when we'll be doing that is the practicals. Okay, we'll also generate error terms. Okay, all the residuals to see how we can model them. Okay, yes. So for the we also have this homoscedasticity, okay, assumption. Then we have the normal distribution of the error term. Okay, so the error term, okay, that is the error term should also follow, or the error terms should follow what? A normal distribution. Or those values should assume a normal distribution. Okay, remember how normal distribution looks like. Normal distribution looks like this. Okay, meaning we'll have some error terms which are high, few will be high, majority will be lying between what? Between this segment, that is that they are within the same range. Okay, and also we'll have few small what? Few small error terms. Okay, so it's like linear, that is a normal distribution. It's like when it comes to exams. Okay, of course, if you do an exam, not all will do what? Will score 100%. Okay, so maybe those who will be scoring that is more than A, okay, all that is, yes, let's say A and above, might be 10% of the what? Of the class, that is of the class, okay, or of the total students. Okay, then 70 sorry, this might be 20%. We don't want to fail most of the students. 20%, then we can say now 70%, okay, of the scores lie, that is or 70% of the total students scored averagely. Okay, maybe they scored a B, and then also we had 10% who are that is underperformance. Okay, of course, even if when it comes to maybe appraisal, if maybe you are being appraised, you are in the same department, okay, and you have been that is appraised. Of course, not all of you will get A. Okay, will have, even if you are maybe, let's say, 20 in your yeah, that is in your what, in your department, definitely the manager cannot give you S. All of you cannot score A. Okay, but you'll find those who are exceeding expectation, who are fostering innovation, they are more creative, they are coming up with new solutions. Okay, so those people can be maybe appraised, like given a higher, or can be classified as what, top performers, and given a score of rating A. Okay, then of course we have maybe those employees who maybe they have, okay, they have come, they have found maybe an existing work process. Okay, they are not coming up with an improved new that is working process. They are just comfortable with that is with the what, with the current uh, working process. Okay, like they are not doing that extra, that is they are not exceeding even though they are meeting expectation, because they are performing, they are meeting deadlines, data accuracy they are keeping, everything it's okay, but they have not exceeded what, expectation. So for this case, maybe they have met expectation, but only few exceed expectation. Okay, then of course you'll have that employee who is also struggling with maybe performance. Okay, they are not doing their best. If you come to attendance, maybe they have some attendance issue. If you come to output, they are not giving their best. Okay, so of course you can now categorize them here. So, and at the end you will achieve a normal distribution. Basically, this is explaining about that is a normal distribution using those two illustrations. Okay, yes, so basically, uh, what we are talking about, or the assumption is that the error term now, okay, the error terms or the residuals, okay, they should what? They should follow a normal distribution, okay? They should follow a normal distribution. Let me try and check in this, that is the example. Okay, we have the residuals. You can see in this data set, you can see we have some residuals which are high. Okay, you can see definitely at some point you'll have some which are what, most of them are low. You can see this, you can see this, you can see this, you can see this. Okay, they are what, they are, most of them now they range between maybe negative 2 and positive maybe 2. Okay, meaning they will be what, on this area, they will be on this area. Okay, and then also you will have other, that is small values of that is the residuals. Okay, like the small values, like this one, you can see negative 0.9 might lie under this area. Okay, this area, that is then positive negative 2 might lie within this area and this area. Also maybe the that is the what, sorry. But if we'll illustrate this best, because in fact I've seen negative 5 is even there. It's even less than than um, than negative 0.9. So like negative 0.5, you'll have those values here. Okay, we'll also have some values which are extremely high. Okay, so basically if you plot all these residuals, they should follow, or they should create a what, a distribution like this. Okay, they should create a distribution that is a normal distribution, something like this. Okay, and we shall also check that. Okay, so if the error terms are not normally distributed, then the confidence interval will be will be either too wide or too narrow, which may cause difficulties in finding what? In finding coefficients. Let me check who is that. Okay, let me just admit Rebecca in. Okay, yes. So, and maybe it can be checked using QQ plot. You can go and research more about this QQ plot. Okay, you can go and that is check what is this QQ plot. Okay, so if you do the QQ plot, if the plot shows a straight line without any deviation, which it means that is the error term is normally distributed. Like you can use QQ plot to do what? To check if the data is normally distributed. If you get that is a straight line without any deviation, then it is a good indicator that the error terms are normally distributed. Okay. Then we have that is the issue of autocorrelation. Okay, basically here we are trying to say the autocorrelation, or we should not have any autocorrelation. Okay, that is within the that is the term the error terms. Okay, so the linear regression model assumes no autocorrelation in the error terms. If there are any correlation, okay, if we have correlation between the error terms, then it is drastically, or it will drastically reduce the accuracy of the what? Of the model. So basically what we are saying is that we should have no that is autocorrelation, or correlation between what? Between the error terms. Okay, we should not have autocorrelation between the individual error terms. And autocorrelation basically usually occurs if there is a dependency between the what? The residual errors. Okay, yes, and that's all about that is the assumptions. That's all about the assumptions that I had. That is notification. Okay. Any question? Any question up to that point?
Yes, sir. Good
Yes.
evening.
Good evening.
Yeah, that was me. My hand was up.
Okay. Yes.
I actually have two questions.
Uh-huh.
One, I would like you to talk more about the confidence interval.
Uh-huh.
And the second one, how can we measure the correlation between residuals?
That is the correlation between the residuals.
Yeah, exactly.
So basically, when we will be performing this model, okay, if we when we'll be performing this model, that is the model will that is calculate it at the back end. Okay, unless maybe we come up with that is a mathematical that is calculation of the correlation, but the model itself, when we'll be returning the output, it will calculate those that is those correlation, okay, of the that is of the of the error terms. Okay, in case maybe within those error terms, okay, for example, if maybe we are having a data set of that is remember the error terms, they are also the residuals. Okay, so if we will be that is using historical data and the predicted data to compare, like maybe for the rainfall we have year one and year two. Okay, so if the error term for year one and year two, or not really, but for that maybe let allow me to do what? To check more on that. For that, I don't want to give you the wrong that is a wrong answer now. Okay, but for the that is for the confidence, interval. Let me also take you that is to tomorrow's that is class, because we have, let me show you, mm, because we still have that topic on the confidence interval, and also there is the output. Yes, during now the that is the during this we'll discuss about, let me just check. There is somewhere where we have that is a confidence interval. It's one of these, yeah, error term. Okay, goodness of it, r squared. Okay, okay. All right. So also for confidence interval, okay, just a minute. Statistical significance. All right. All right. Okay, so mostly for confidence interval, of course, we'll discuss it when we'll be discussing as well as the degrees, that is the degree of freedom. Okay, degree of freedom, and also confidence interval when we'll be dealing with what? When we'll be talking about that is the R square, because under R square is where now, like, at what interval do we do we um, take our model? Okay, if we are taking confidence in interval of maybe 95%, if it is of 99%, remember for that is for that is confidence level. For normal research is always 95. When we are talking about that is talking about medical experiment, we talk about 99%. And yeah, I guess it's only 95 and 99. So we shall talk also about that, because of course before we run this that is outputs, okay, we'll also discuss about the confidence that is interval and level. Okay, for that you'll allow to me that is to discuss tomorrow. And then about the second one was that is it was that is how do we calculate those, that is the error term, or how do we calculate the correlation between the error terms. So for that, allow me to give you a feedback tomorrow. Okay.
Yes, no problem. Yeah, problem.
Okay. Okay. Yes, Daniel and Melas.
Yeah, thank you. So my question would be on that normal distribution of error gamma. What do we read as the highest value on that curve, on that normal distribution curve?
So
Is it the
it changes with
median?
what? With the type of data you are using. So maybe if we will be using the that is the what do we call, like the umbrella data, okay, we will get a different like error term. When you are using maybe the income data, okay, it will also give you different, that is different value. Okay, because remember about the error term, all the residuals we've said, they are what? The actual data set minus that is the predicted, minus the predicted, okay, minus the predicted value. Okay, you will get now those error terms. Okay, so these error terms, they vary between what? The predicted values and the what? And the actual values. And the actual values, they might that is change, that is between model and model. Okay. Daniel?
Yeah, but maybe not yet home.
Uh-huh.
So, on that highest point on that distribution,
Mm-hmm.
where you read like 10%, they got A. On the bigger part there, they got maybe 7, and the others on the right far end, they got 10. So,
Mm-hmm.
what about that on that big gap? Maybe you can go that to that normal distribution error term,
Mm-hmm.
that linear representation. Like yeah, for this, where you've written now letter B on that highest point, what they like, how do you read that? Would that be the mean or the median, or how would you read that the highest point on that distribution curve?
So if maybe we have, if the data is perfect normal distributed, then the highest point here, definitely it will be the mean. Okay, that's why we
That
are saying even because we'll have that is very many scores between here. Okay, very many squares between here. That's why we are saying it is average performance. These are, they have, maybe they are average performance, these are top performance, these are low performance. Okay, but if we are talking about, like for example, if this side, the that is, we are taking that is 10% and this 10%. Okay, so basically like you can see, we can now divide this part into what, into two equal sides, meaning maybe from here and here will be maybe 40. Okay, and here will be what, will be 40. So basically if you do that is, you calculate the mean, it will calculate this, or it will separate this normal distribution into what, into two equal parts. Okay, and in this case, if whenever we have like that is a perfect normal distribution, we usually say mean at this point, we usually say mean is equal to median is equal to mode. That is for perfect normal distribution. We shall check that when we will come to that is distributions. Okay, we'll come to see that when it comes to that is the distribution. Okay, the normal distribution. Uh, Okay, yes, you can see when we will come to say this, like in a normal distribution, that is a perfect normal distribution, the mean, median, mode are equal. Okay, but we shall check that is on those different that is what do we call them, properties. Okay, so in this case, if the that is the two teams are maybe fairly performing well, then you can now separate them into what, into two groups. Okay, but this is majorly when we will be you will understand it better when we'll be discussing about normal distribution.
okay, thank you. Then I think you might have answered my second question, because I would have asked, what would that mean if this normal distribution, when now you point out the mean, if it's not symmetrical, that is portion A on the highest performing and portion B on the lowest performing, if it's not symmetrical, say in here, you'll have a much more almost nearing the x-axis, but on the other option of the 10%, the other is not performing. Maybe it might be way having a bigger gap on the x-axis. What would that mean?
Yes, so like when that, like for example, if maybe we are talking about symmetrical distribution, it means that the that is, like we are separating. Okay, that is the y-axis. It's like separating this normal distribution into two equal parts. Okay, but if maybe that's not the case, then it might mean we have what, we have some that is our data is somehow skewed. Okay, our data is somehow skewed. That's when we'll talk about skewness. Why? For example, if we are saying about we are talking about 20, okay, percent, and what, 70% and 10%, 10%, meaning we'll have, that is our tail will be longer, okay, on the what, on the left, okay, on the left side will that is our tail will be longer at that is on the left side. Why? Because on this left side we have high data values in comparison to what, to this side, because here you can see we are only talking about what, we are only talking about 10%, okay, and here we are talking about 20%. So let's assume we are dealing with that is 1,000 people. So basically 20% of 1,000 will be here, and you can see here we'll have more data compared to when to this side. So in this case we might say, even if our data follows a normal distribution, it might be slightly skewed, okay, to the left. But I will exhaust that. I will exhaust that during that class.
Okay, maybe the last question. So that would mean we have many outliers on the side of 20 or on the side of 10%.
No, not to say like outliers as such, okay, but of course yes, we'll have more data values on the that is on the left side, in that is compared to the right, that is to the right side.
Thank you. Thank you.
Okay. Yes, Milas, so that I may close if you have.
Good evening.
Good evening.
I have about three questions. My first question: what would be the actions when there is no linear relationship between two variables? Are there any transformations that we can do on our data in order to make them linear so that we
Yes.
can deal with our linear regression model?
Yes, you can use log norm. That is it. Log. Like for example, if your data was exponentially distributed, like it had the exponential what? Let's say maybe my model was y is equals to that is exponent. It was an exponent, meaning that is between y and x. There is no linear relationship, right? So in this case, we can just that is introduce log. Okay, we can introduce log. Okay, to do what? We can introduce log to that is to make our what? Our model, okay, to be linear. Okay, like for example, now it will be, if we do a log, we apply log everywhere, then we know we'll have log y, okay, as our output, and then that is, we have log exponent of x, so it will be x, okay, log of exponent minus 1, okay, plus log of c. So you can see in this case now, this becomes a constant, okay, this becomes a constant of x, and this becomes a constant of like of the y-intercept. So in this case, you can see we've transformed that is this model to what? From nonlinear to linear. At least we've given that model what? That is a linear relationship. Just an example.
Okay, good. My second question. I imagine that for the coefficient of determination, if all the data points fall in the regression line,
Hmm.
then the coefficient of determination will be 1.
Will be, yes, will be maybe nearing one, because
Yeah,
it's rare to have that is like all your data points to be along the regression line 100%. It's very rare.
yeah, it's very rare, and I'm thinking that for us to have a better coefficient of determination, the first step is to remove outliers.
Correct. You, mhm.
Assuming that we have removed all outliers, but still our coefficient of determination is still less than 0.8. Is there anything to do next in order to make our model fit well?
Yes, maybe. So if it's still, if it's less than 0.8, definitely it means you have to find another what? You have to find another that is another independent variable. You have to use another independent variable, or you have to go back to the field and that is collect more data. Okay. Let me try and see. Mm, don't know where those. That is. Don't know where I have those notes. I don't know if it is in this or it's in another. That is. It's another in another notes. But what I know is that if that is if you are that is uh coefficient of determination is what? It's less, okay, or it's less than 0.8, okay, then you will have to do what? You will have to you will have to find another independent variable, okay. If it is at all, it's less than 90, let's say 90, let's say 80%, you'll have to find another independent variable, or you'll have to check maybe your data points. Okay, you'll have to check your data points. Yeah, that's okay.
Okay. My third question, I would like to know whether there are any metrics that we can check in order to see whether there is no violation of the assumptions that we have seen. And in case there is any violation observed, what would be the action?
So for the assumptions, so when it comes to checking the relationship, checking the multicollinearity, definitely here, we are talking about correlation here. So you can use correlation for the first two, okay, to check if that is the correlation, um, to check their correlation as per what we've talked about. Then for homoscedasticity, maybe you will have maybe to, after you have run. So this you can see, like this is coming more after you've done what? After you've done maybe those like prediction, or you've already done what? You've already that is fitted your model. Because where will you get the residuals? Where will you get that is the error terms, if at all you have not performed all this? Okay, you can see here we are talking about error term, we are talking about error term, we are talking about error term. So for this one, is it acts like a check, okay, it acts like a check more so when you've done that is your model. It's basically to show you, yes, we've fitted, that is our model, okay. It might, maybe might our model be showing maybe some attributes on linear regression, but not obeying them. Okay, so for that, now these ones you can do before you can do your conclusions. Okay, also to check maybe the model if it's actually a linear regression model. Okay.
I don't think I'm satisfied with your answer because, of course, we can check these assumptions after fitting our linear regression model.
Uh-huh.
After fitting the linear regression model and we find that one of these assumptions is violated, I would like to know, do, can I use my model to predict, to do my,
So
do I need to find another model to use? Do I need to do some more adjustment, maybe for me to have, for these assumptions to be uh, not violated? So I need those kind of answers.
so like for example, let me just tell you. So in case maybe where we find I that is alt I multicollinearity, okay, is it an issue? Okay, is it an issue if like to discard a model, okay, when we have that is multicollinearity? Okay, the only that is disadvantage with multicollinearity, it's not about prediction. Okay, of course we have that aspect of prediction. Why? Because you will not be able to measure if you are working with more than two variables. You will not be able to know, okay, which variable is affecting what your output, maybe majorly, okay, and which one is not affecting that. Like it will be difficult for you to determine the independent variable affecting what, affecting your output. This is the advantage of multicollinearity. More so if you want to see which is the fact, like for example, if you are dealing with that is with hospital data, okay, you might try to see what factors contribute to high blood pressure. Okay, is it obesity? Is it maybe like obesity? We have what else? Poor diet. Okay, you can see those are features. All those are factors. Okay, so if these two factors are what are highly correlated, you will not be able to know, is it obesity? Is it poor diet, which is bringing about this high blood pressure? Okay, so in that case you'll have that challenge. Okay, so that's why it is good also to check that. Okay, when we are talking about maybe homoscedasticity, we are saying that that is the error term is this is the same for all values of independent that is values. Okay, when will you check this? More so, let's say as let's assume when you do what? When you run your model, okay, and get maybe that is the uh, coefficient of determination is very small. Okay, definitely you will have to do some investigation. No, which maybe assumption might be affecting our model. Okay, and how can I correct that one? Okay, if it is maybe if the like let's say the for example the error terms are what are no, the error terms that is are not normally distributed. Okay, this means maybe we might having our data with that is with what, with this kind of outliers, or the data has many outliers. Okay, so in this case you will have to go and do what, correct your data set for you to improve on what, on your model performance. Okay, if it is the issue of that is homoscedasticity, okay, you will see That is, if that is your value of the same pattern, that is your error term values have that is same pattern, or they are scattered all over. Okay, so with that, of course, it will affect. If you find it is more of heteroscedasticity, definitely it will what? It will affect your output. Okay, so with that, you will have to that is do maybe some control measures. Okay, you can even go and research more about that is the correct measures of, in case maybe homoscedasticity assumption maybe it's violated. How do I correct it? Okay, you can go and even research on every that is assumption. Okay, see, like for example, the way we've done for the exponential that's a relationship. Okay, we've corrected it and we've made it to be what? A linear. Like, you check each assumption and see how you can correct its measure. That's an assignment. Maybe you can go work extra mile to get that that is the to get that reason. Okay,